Back again. This video is all about ground source heat pumps, how they work and how to install them. So if you're very negative about ground source heat pumps or heat pumps and you've heard some really bad rumours about them, they are good. They are absolutely brilliant. They're the future. If you're in an area where it's LPG or oil, heat pumps are by far better. They're more efficient, sustainable option, and they're cheaper to run. So when it comes to having a heat pump, it's all about how to use them. So for example, with a ground source heat pump, they will work more efficient, constantly working at low temperature. So with a ground source heat pump, for example, they're most efficient and better off being designed with an output temperature of say 35. So 35 degrees, the radiators or the underfloor will be on all the time. So you have that fitted with load compensation, weather compensation, you've got a very efficient system. With it being designed at 35 degree flow temperature, the house will be constantly warm. Now, if you're a dinosaur and you've got a back boiler, coal or LPG system, you put your heating system on and you expect the radiators to be scalding hot. Heat pumps don't work like that, I'm afraid. If a heat pump is designed correctly and you fit a good manufacturer, a heat pump will come with 7 or even 10 years warranty. So you're getting reliability there, efficiency there, and they're cost effective. So, very interesting video coming now, ground source heat pumps. I want to talk about the heat pump, the components, and actually how to install the ground source collectors. I have done quite a few heat pumps now. I need to sell the actual collectors in the ground. So, hope you enjoyed this video. Any questions, put in the comment below. And don't forget, ground source heat pumps, there's not a great volume in this country, and it's new technology that we all need upskilling on. So if you can add to the knowledge in this, comment. Any questions, comment. Don't forget, you're at the WOW website, loads of information on it, and it's all free. So as you can see, it's all accessible. All the sides have came off. Underneath you've got anti-vibration feet. It's really good insulation on this. Look at that. You've got handles to help maneuver it. Ground source heat pump is kind of a system boiler, so you got your collectors from the ground going in there, primary hot water circulation to your cylinder coil, that goes to the expansion vessel, heating, flow and return. What I like about this is it's a generic interface. It's the same as the boilers, same access code to get in. And let's have a look at the electrics. The electrics on this is actually quite daunting. Look at the size of the PCBs. It's got its own mini circuit breaker. The good thing about this, it's got switching for the controls, 24 volt, 240 E-bus. But the best thing about using E-bus, there's no calm, normally closed, normally open. The boiler and the controls do everything for you. Yeah, so I like that. Remember, when you're doing E-bus wiring, you always have 25mm separate from other cables to stop any turbulence. So this is the plate to plate. This is where the brine side comes in. 30% glycol mix comes in, and just here you've got the Wilo pump. So in renewables, what you'll find is people prefer Wilo pumps because they function better with glycol and at lower temperatures. So you can tell it's the brine because it's heavily insulated. Just here we have a drain of flush point. So as it comes through in the plate to plate, The other side is the refrigerant. So the refrigerant comes in to the compressor lug. So it's a Copeland compressor. These are pretty popular, Copeland. This is a scroll compressor, and I'll explain later how a scroll compressor works. If it was an air source heat pump, it would be an inverter, and you'd have trace heating at the bottom. So this component and that component are electronic expansion valves. So what they do is they release pressure. So for example, this might be low pressure and this might be high pressure. So it just releases a small amount of pressure to keep the high and low at a greater distance. And these just pull off. These very rarely go wrong. There you go. So it's a solenoid. Never take these off and function them because they will burn out. So always make sure you put something in the middle of that. Here we have Schrader valves. That's for charging the refrigerant up. This is a pressure switch or sensor. So if the pressure is too low or too high, this will switch off. I think it's the lowest is about 7 and the highest is about 32. And here we've got 2 more pressure sensors as well, look. So this is to direct it between hot water and heating. Take it off, there you go. Hot water side, heating side. Right then, here we go. At the back, underneath it, we have a 4-way valve. Can you see? So what that 4-way valve does, it provides a reverse cycle. So let's take, for example, if you need to do a defrost cycle, it will send the circuit backwards. Just here we have a supplementary heater. So a supplementary heater, it wouldn't really get the house hot, but what it would do, it would take a freezer off. So it would make it comfortable, shall we say. So this has 3 elements in, a 2 kilowatt and 2 3.5 kilowatts. Central heating circuit pump. Drain and flush point. The condensate. So this obviously translates the heat from the fridge side over to the heating and hot water circuit. You can see there's 2 different metals here. That's because 2 different metals expand at different rates. That tends to knock scale off. So another useful component to note here is the dryer or the filter. So the refrigerant gets heated up through the brine plate, and the heat then goes to the other plate, and the refrigeration comes through here. You can just see it there. That is a dryer or filter. So what that does, that prevents any dirt or liquid or water actually getting into the scroll or compressor. Another one to point out, there is a water pressure sensor on this, just at the back there, as you can see, look. That's the same as in the boilers. To the right, we've got a dry pocket NTC. There's also another one on the fridge circuit. That's just to monitor the temperatures going around the product. Another angle is the scroll compressor, fridge in, fridge out, high pressure sensor, and just above there you can actually see the four-way valve. So, preheated by the brine side, goes to the plate at the back, goes to the compressor, vaporizes, heated up, pressurized, goes through the other side of the condensation. And here is the ground source heat pump schematics with all the components in. So ground source efficiency is calculated on the brine 0, water 35 degrees, and here you got the plate to plate. So the brine comes in, glycol comes in, and basically what happens is the temperature of the brine comes in, evaporates the refrigerant. So you got the pump. The brine side can have an expansion vessel, but sometimes what you get is huge containers, and they're clear so you can see the water level, so you can actually top it up by hand as well. So the brine water comes in, vaporizes the refrigerant. Here you have a low pressure sensor. Here you have an electronic expansion valve, and that maintains the pressure, keeps it low or high. So the electronic expansion valve, if you want to test them, it's a solenoid. You take the head off and you can put a magnetic filter on it. And I'll do a demonstration now. So EV expansion valves, this is a solenoid, but it's the same principle. To test them, pull them off and put a magnet over it and see if that charges it. Just here we have something called enhanced vapor injection, and this is so the heat pump can achieve higher temperatures. So it goes from vapor to being pressurized, and then that vapor goes through the process again with more refrigerant. The reason why this happens is to enhance the process and increase the temperature of the refrigerant. Here the vapor comes along. This is a dry filter. This is to protect the compressor, so it prevents solids or liquids damage the actual compressor. This compressor is called a scroll, and a scroll compressor squeezes the vapor. This is what a scroll compressor looks like inside, and there's windings inside, and basically it squeezes the vapor into high pressure. So the compressor heats the vapor up and increases the pressure. So the vapor comes through here, 70 degrees, and here the plate to plate actually heats the water up going to the premises. So as the vapor comes in here, all the warmth is absorbed from it. All the warmth is absorbed from it, so it goes from a vapor to a liquid again. So basically, it goes through a condensation process. It's like a window. This is the central heating circuit of the plate to plate. So it comes in, you've got the pump, you've got a drain point. The water's heated up here, but then it goes to a W plan. So what a W plan is on the heating system is where the hot water gets priority. So the hot water cylinder here is heated at 50 degrees, and you'd have a Legionella boost on that. So it's a mid-position valve, W plan, priority hot water. And the reason why you have priority hot water W plans is so when the hot water's reached temperature, you can then decrease the flow temperature for your heating. Your heating, you can have it at 35 degrees for treble radiators or double-sized radiators, or you can have underfloor. Underfloor will be about 30 degrees. Here you have a four-way valve. So, most heat pumps have a four-way valve, and it creates a reverse process. So what happens here is the refrigerant comes through, goes in, comes out, goes to the compressor, comes out the compressor in the top of the four-way valve and back to heating plate. In reverse sequence, the internal will move to the right and the compressor will put a reverse sequence in. So it'll pump it round and back through the plate to prevent any freezing. And that's the same as the air source heat pump. It will do a reverse cycle of the refrigerant to prevent freezing. On the plate, for the heating side, on the flow, you'll have a pressure sensor for the heating system, and you'll also have a supplementary heater. So if the compressor or the heat pump was to fail, you still get heating. Compressor, you have two sides on the heat pump, a low side and a high side. On the high side, you have another pressure sensor. So the low and the high will monitor the performance. So recap in brief, the brine temperature vaporizes the refrigerant. The compressor increases the temperature and pressure. It goes to the plate and it then absorbs the heat, makes it a liquid again. What you can get on ground source heat pumps, on the brine circuit, you can get a passive cooling system. So the brine circuit will come in here and it will go to a plate. It will be then pumped around the property or the commercial unit to provide cooling. You have to be careful with this because I've seen it actually freeze tiles and pipework. So brine goes in the passive cooling unit to provide cooling. This is very cheap to run, very efficient cooling method. So now let's talk about the ground collectors, what types they are and the key features to getting the optimum performance out of a ground collector. So the first type is the horizontal ground collector. Now these are best 0.8 meters apart, centre to centre, and really they want to be between 1 and 2 meters down to get the best efficiency. So 2 meters, you could get 12 degrees plus out of the ground. That's free energy. And the good thing about ground collectors, it's regular, it's constant, no matter what. If it's cold, raining, snow, you're still going to get that temperature, that heat source from the ground. The type of earth that you want is best damp. If it's dry ground, if there's stones in it, avoid it. You're not going to get any heat input from it. The next type is the slinky method. So, a slinky method is where the pipe goes round. And these can be done horizontally and vertical. And these, by some manufacturers, are avoided because they tend to lap over. 1, 2, 3, 4. Okay? So some manufacturers do not prefer those methods. So the next type is the ground collector panels. Similar sort of thing, the 2 meters in the ground and the columns, the parallel columns. These are very good. The only downside to these is that there is joints in the ground. You want as least amount of joints as possible in the ground. So next test you can do if you're going to use ground source collectors is a TRT test. That's a thermal response test. And basically what happens there is it puts low voltage in the ground. And as it disperses it in the ground, how quick it disperses that voltage is how conductive the ground is. So let's say, for example, if it was to disperse 24 volts DC, if that voltage was to be lost in the earth, it's damp, it's wet, and it's going to conduct the heat into the pipes. So for some boring stuff, when you first install your ground collector, always put sanitizer in it. What that will do, it will flush out the ground collectors, any mud, sludge, oil, dust that'll come out. Glycol, you put glycol in to prevent it freezing, and that is a 33% glycol mix. And you use ethylene glycol, it's more friendly. And you purge it. You purge it for 50 minutes. The reason why you purge it is to eliminate any air that's in those ground collectors. If there's air in it, bacteria will form. Sorry. R1, so these are the types of ground collectors that you have, and these are sometimes used in formulas. So R1, that's a horizontal collector. R2, that's a ground collector, so basically the ground collector is going down and back up again. R4, that's a slinky ground collector. Can you remember? It's the one that's not really recommended. So overlaps 1, 2, 3, 4. So for ground source collectors, especially if you've got several loops in the field, you've got to have a chamber. And the chamber is good for flushing, flow rates, and it's good for distributing the glycol out there as well. You can purge it from there. So this is a bit about the chambers. So chambers are usually circular. You can't get them rectangular. So usually when you get them, the pressure tested, they're usually filled with water and check for leakage, because if they're in the middle of the field, you don't really want them leaking and contaminating inside. They're usually white or black. There's usually a sump or drain point, so there is a leak, you can drain it out. Usually when you connect onto them, there's usually an knob to send the pipe down, so it's not strained. So it goes inside to a manifold, and there it reduces down. With these, they're always sealed, so there's usually a huge O-ring that goes around the top. Regards to the lids, you need to get the correct variance. So if it's in a field, you've got to think about foot traffic. If it's on a road or driveway, you've then got to think about vehicle traffic. And whenever you connect these up, you use fusion welding. So you get a welder, you can usually hire them out. You need to think about the watts of the welder and the time. And usually whenever you, prior to welding, you deburr it. You can use a cleaning chemical, and you place it on and you clamp it on. You put into the machine the wattage and the time. So inside the chamber, here's the chamber, you'll have the manifold, which will come in and it'll reduce down to distribute to the loops in the ground. So usually the top ones will have the isolation valves. The bottom circuits will have the isolation valves on, but they'll also have flow limiters on, so you can monitor the flow rate of the system. So in Holland, they have vast amounts of ground source collectors, but they're usually boreholes, and they're usually in a block of flats, and they provide district heating throughout the community using heat interface units. Here in the UK, ground source boreholes are more really up north, more common in places like Scotland, because the ground is wetter and it's easy to drill. Down south, the ground's tougher, less conductive, and it's harder. So, things to be aware of. When it comes to ground source collector, you can put them in grout. Grout, that just enables the ground collector, the borehole, to conduct the heat better. They're usually 180mm wide. At the bottom, you have an anchor, like a weight, so that when you're dropping the collector in the ground, it will pull it down. Really, it needs to be about 2 meters. Well, 1 meter to 2 meters. Fusion weld fitting the top, and that is usually in some form of chamber, so it's always accessible. And at the top, the difference between the flow and return needs to be 3 degrees. Between the ground source boreholes really needs to be about 50 meters. There are instances where it draws that much heat from the earth, it dries it out. And sometimes what can happen is when there's a frost or a freeze, when it's thawed out, the frost and the snow is still there because the ground source is just drawing all the energy. And that's usually when it's been oversized for the ground, or maybe undersized for the heat pump, and it's just drawing it out like ponds and water collectors. So the next type of collector we have is water. So when you're using water to collect heat for the heat pump, you need a license and you need to do a flow check. So you need to check that it's not going to freeze, and you need to check the heat and the water can easily be replenished. So here we have open type, where it just takes the water actually into the collector, into the plate to plate. Here you have 2 closed circuits. This one's a slinky method, and this is a loop. So this one here, this simulates pieces of pipe. So what you can do is you can get pieces of pipe, ground source collector pipe, even waste pipe, 1 meter long, drill 2 holes either side and fill them with cement. And then what you do is, as you row out into the lake or to the river, you tie them using tie wraps to the collector. This method is pretty good because with a meter long concrete securing separators, they actually drop the collector to the bottom of the lake. This slinky method here, people tend to just put them in the lake, and then when they fill the system with glycol, they wait for it to drop. But the problem is, if you're ever working on this system, you get this air in or you drain it, what's to say it's not going to float up again, or it's going to get caught, because obviously slinky can be quite deep, can't it? But this type I actually prefer. So there was a really interesting install in Europe recently, and basically there was a high-rise block of flats, and inside each floor there was a mini geothermal unit. Now this small wall-hung heat pump was actually the same size as a gas boiler casing. In fact, it was in a gas boiler casing, and so it was a little boiler heat pump, wall-mounted. It was only about 3 kilowatt, and it did several radiators, and it also did a cylinder. And these were on each floor. And basically what happened was there was a ground source collector unit that went into a local river. It came up and fed off to the wall heat pump geo units. And in this experiment, the field trials were absolutely superb, the results, because what they found was, as the ground source collectors came up the block of flats, the warmth from the flats made the pipes sweat and actually gain more heat. So mini geo units, wall hung, they were a huge success in Europe, and maybe these are the actual future. Ideal. All you got to do, heat, 4 radiators max, hot water, fantastic. And this is how they do it in Europe.